Okay, hello everyone. I am Ankur Haldar and welcome again to the playlist from high school to physics. This is the second lecture of the series, and this lecture is about relations. And I hope you have watched the previous video. And I think I'm assuming that you all know what a set is and other details that I covered in that video, including Cartesian product before learning relations. If you have forgotten what a Cartesian product of two sets is, then I highly encourage you to go back and revisit the portion and then come back. Okay, so let's start today's lecture. And today we will be talking about relations and what is a relation and how will I define a relation in set theory. And one thing you need to remember, I'm not teaching these subjects pretty formally. If you want to learn these formally, then you have to delve deeper into the topic, and I'm just covering the basics that you need to know after completing high school. And yeah, that's all. So before learning relation, let's consider two sets. Suppose this is a set. I'm denoting I'm making a diagram like a Venn diagram, and suppose these are some elements of the set. Okay, suppose this is set A and these are some elements. Okay, let's name them. This is 1, 2 and 3, and here I have another set, and suppose I have 4 elements here, and let's name this small a, b, c and d. And we are interested to know if there is a relation between any two elements of between these two sets, and we are not interested in how they're related, but we are just interested if they're related or not. Okay, suppose I have suppose 1 is related to A. Okay, then and suppose 2 is related to C, and it can also be possible that it is also possible that 2 is related to D also. Okay, so yeah, so how will I write these types of things mathematically? Okay, so I can write that 1 is related to A, I can write like this, 2 is related to C, I can write 2 is related to D, or you can use a different notation. You can use 1A, 2C, 2D, whatever you like. But I'm following the most used denotion in literature, that is using a first bracket and a comma. So when I'm writing this 1 and A within a first bracket and with a comma between them, that means that 1 is related to A, and like that 2 is related to C and 2 is related to D. Okay, so I will be using particularly this type of notation. You can call this a tuple notation, because anything within a first bracket is called a tuple with comma in between. So if you know programming, or if you do programming, then you will be then I hope you are familiar with the word tuple. But if you are not, then don't worry, it's just the structure, and it's a non-immutable structure. That means you cannot add anything inside a tuple after you define it, and you cannot take out anything from a tuple after you define it. So when I'm writing 1 comma I, that means that this tuple is 1 comma I, you cannot change it. That's a formal definition, but we are not interested in that. Okay, so I hope you are getting some familiarity with Cartesian product with this notation, right? So let me clear the mist. And yeah, so I will be giving a definition of relation, not that formally, because yeah, I will just say that a relation okay, let me see the note. Okay, a relation from set A to set B is a subset of the Cartesian product of A and B. Okay, Yeah, I hope you are familiar with Cartesian product. Yeah. So let's consider A is 1 and 2, and let's consider B is A and oh, I'm using a wrong notation here. Sorry for that. These are not first brackets. These are third brackets. Sorry, these are second brackets. Yeah. So A is a set containing 1 and 2, B is a set containing A and B. So my A and the Cartesian product between A and B will be 1 comma A, 1 comma B, 2 comma A, and 2 comma B. Okay. So any set R which is a subset of A cross B, that means it can be only 1 comma A, it can be 1 comma A and suppose 2 comma B, and so yeah, so this relation tells that 1 is related to A, this relation tells that 1 is related to A and 2 is related to B, and yeah, so there can also be a relation that is nothing, that just contains, oh, I wrote a little wrong here. Yeah, so there can be relation that is the null set itself, and because null set is also a subset of every set, so yeah, this can also be related a relation, and this tells that no elements of A is related to no elements of B. And so there is another concept that suppose I want to know if the elements of one set is related to themselves or not. Suppose I have a set A 1 2 3. I want to know if there is a relation between them or not. And then what will I have to do? I will be figuring out the Cartesian product of A to itself, and I will say that if there is a relation, that relation will be a subset of nothing but A cross A. Okay, so let's discover, let's find what this can be. So I'm taking a basic example here. Suppose A is 1 2 and 3, and so my A cross A will be 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, and 3 comma 3. So the reason I have written this in particular this format, there is a reason behind it. I will be explaining the matrix representation of a relation, and it will come handy then. And yeah, I will be explaining this in a moment. And so a relation that goes from A to A will be a subset of this huge set A cross A. Okay. This is as simple as that. Okay, if now I will be telling some basic classifications of relations, but before that I want to explain two types of representation that we can use. Number one is matrix representation. Matrix representation. Okay. So what is a matrix representation of a relation? Suppose my relation contains this, and this element. Okay. Then I can represent my relation like this. That means that this element, that means that 1 comma 1 is present. This element, that means 2 comma 2 is present. This element means that 2 comma 3 is present, just like that. Okay, and it's as simple as that. So I think you have got it. And if this is also present in the relation, then this will not be 0, this will be 1, and just like that. And this is my matrix representation. A matrix representation is represented by a matrix, and suppose ith row and the element in ith row and jth column, and that signifies the relation between the ith and jth element of A, this relation, right? So you can see, suppose I'm taking example of this, it is in the second row and first column, and it says it's saying that the second element and the first element is related, just like that. So this is the matrix representation. So this is the yeah. And number 2 is digraph representation. Let me see if the term is right. Yes, it's digraph representation. Digraph. Okay, so it's digraph representation. What is a digraph representation? We are saying that suppose the 3 elements are 1, 2, and 3, and 1 is related to 2. That means 1 is related to 2. We are writing like this, and 2 is related to 3, so that will be this. And suppose 1 is related to 3, this will be like this, and this is 1 comma 2, this is 2 comma 3, this is 1 comma 3, and suppose 3 is related to itself also. So yeah, this will be my 3 comma 3. So this is a digraph representation where the elements, we denote the relation, the elements of the relation set with little arrows. Yeah, so this is all. So I will be explaining some classification of relations using both matrix and digraph representation, and if applicable. Let's see, I have not written everything here, but I will try to cover everything. Okay, so number one is empty relation. Empty relation. Empty relation is what? Empty relation is nothing but the relation phi. It has nothing in it. Okay, the diagram. One thing to remember, that I will always be talking about A as the set to be 1 comma 2 comma 3. Oh, once again I have written first bracket here. This will be set. Yeah. So yeah. So here the digraph representation will be like this. There will be no arrows between them, and the matrix representation will be like this. It will be a null matrix. There is no element. There is no element because there is no relation, right? So this is empty relation. This tells that no element of A is related to no element of A. And let's go to the second one. The second one says identity relation. Identity relation. Yeah. So what is this? This says that each element is related to itself and not to any other elements. Okay, so how will it look like? Suppose we have 1, 2, and 3. So 1 is related to 1, but it is not related to 2 or 3. 2 is related to 2, 3 is related to 3, and the set will be like this: 1 comma 1, 2 comma 2, 3 comma 3. In a rooster form, this will be like this: A comma A, such that A belongs to my main set A. Okay, and in matrix representation, this will look like just like the identity matrix. Okay, so this is identity relation. Okay, now next one. I hope I have I have covered. Yeah, so now next one. The next one is universal relation. Universal relation. What is this? And this is nothing that in this relation R contains every possible relation. That is, R is the Cartesian product itself. So a digraph representation will be a mess. So let's draw it. So 1 will be obviously related to 1, 2 will be obviously related to 2, 3 is also related to 3 itself. 1 will also be related to 2 and 1 will also be related to 3. And 2 will also be related to 1 and 2 will also be related to 3. 3 will also be related to 2 and 3 will also be related to 1. So I think this is the whole picture. And so the digraph representation looks like a mess. So the matrix representation will be helping us out here. So this look like all the elements is 1 because every relation is present. Okay. So that's why we use two different representations. Sometimes the digraph is like a mess. Sometimes the matrix is hard to construct. Then we will try to use one another times. And it's not that important which one you use until, yeah. So this is a universal relation. And the next one is reflexive relation. Reflexive relation. In a reflexive relation, if in this relation every element of A is related to itself, then the relation is called reflexive. And what does that mean? That means that in this relation, and I'm writing the matrix representation, these three elements must be present. And you will be wondering that this is just the identity relation, right? But yeah, identity relation is also a reflexive relation. But the difference is a reflexive relation can also contain other relations than the identity elements. Okay, it can contain this element, it can contain this element, and it will still be called reflexive relation. Okay, and we don't care if 1, 2 and 3 is related to one another or not. We just care if it is related to itself. If they are related to themselves, then we are calling the relation reflexive. And we don't care if one is related to 2 or 3. It doesn't matter to the reflexive parameter. Okay. So yeah, this is a reflexive relation. And now we are going to learn about symmetric relation. Then what is the numbering? 4 of it should be 5. 5. Symmetric relation. Okay, a symmetric relation, it implies that if a relation A comma B is present in the relation, this implies that B comma A will also be present in R. Okay, it's yeah. So this is all. If A comma B is present in R, then B comma A will also be present in R. So in matrix representation, let's see, if suppose if I have this element, this is 1 comma 2, and I must have this element also, 2 comma 1. And if I have this element, then I must have this element also. So this is a symmetric relation because the matrix look like a symmetric matrix, right? So this is a symmetric relation. And a symmetric relation in digraph representation says nothing but this: if 1 is related to 2, then 2 will also be related to 1. And if 1 is related to 3, then 3 will also be related to 1. Like this. It's nothing else. It just tells that if one element is related to another, then that other element will also be related to the first one. So this is a symmetric relation, nothing else. And let's go to the next one. It's called the transitive relation. It's called what's the numbering? I'm forgetting. It's 6. Transitive relation. A transitive relation. Transitive relation, what does it tell? It tells that if A is related to B, this belongs to R, and and B related to C is also in R, and we write and like this, then it implies that this is also is an element of R if R is transitive. Okay, so it says that if 1 comma 2 is in R and 2 comma 3 is in R, then 1 comma 3 must be in R for R to be transitive. And how do we depict that in matrix? 1 comma 2 is this element, 2 comma 3 is this element, and yeah, and 1 comma 3 will be this element. So this is a transitive relation. This looks like an upper triangular matrix, but yeah, I don't think it has a direct relation with that, but yeah, it looks like that. Yeah, yeah, it looks like small triangles inside the matrix, but yeah. So in digraph representation, it is more intuitional. If 1 is related to 2 and 2 is related to 3, then 1 must be related to 3. Okay, so this is a transitive relation. And now the next one is equivalence relation. 6, now 7. Equivalence relation. Equivalence relation. Equivalence relation says that a relation R is said to be equivalence if it is reflexive, symmetric, and transitive. Then it's called the equivalence relation. Okay, so what does that mean? Suppose I have my matrix in matrix representation, the relation has to be reflexive, so the diagonal elements must be 1. Okay, and the relation also have to be symmetric. It also has to be symmetric, so if this element is here, then this element must be here, and it also has to be transitive. So look, this is a transitive matrix because here 1 is related to 1, 1 is related to 2, and 2 is also related to 1. That means 1 is related to 1 also. So yeah, this signifies a transitive matrix also. So this because 1 is related to 2 and 2 is related to 1 and 1 is also related to 1, so it's transitive, right? So in diagraph representation, this look like this. 3 is related to 3 itself, 2 is related to 2, 1 is related to 1, 1 is also related to 2, and 2 is also related to 1. Another example of equivalence relation is this one. Okay, so we have the diagonal elements once again. We have 1 comma 2 and it has to be symmetric, so this element must be there, and we also have 1 comma 3, so this element has to be there. It's we have 1 comma 3, so and this the universal relation. So this is also an equivalence relation, right? So because it satisfies all the required condition to be an equivalence relation. Okay, so now the final one, sorry, I forgot the numbering once again. It's 7, so after 7 it's 8. The antisymmetric matrix. Sorry, not matrix, relation, my bad. Antisymmetric relation. It says that if A and A comma B is an element of R, then B comma A is also an element of R if and only if A is equal to B. So if 1 comma 2 is an element of R, then 2 comma 1 cannot be an element of R for R to be antisymmetric because they are not same. But 1 comma 1, if it is an element of R, this can imply that by interchanging them, this is also an element of R. Okay, so how will I write this? Suppose there's an example R is 1 comma 1, 2 comma 2, 3 comma 3, and 1 comma 2. In matrix representation, this look like this. So this is reflexive, right? Yeah, because all the elements are related to itself, and it also has an element called 1 comma 2. 1 is related to 2, but the vice versa is not happening here. 2 is not related to 1, so it is anti-symmetric. Okay, as simple as that. And you can say, yeah, it's just like that. Okay, but these things are allowed. 1 is related to 1 and vice versa is 1 is related to 1. So yeah, an antisymmetric relation can also contain elements like this. So yeah, yeah, so these are the types of relation, and I have oh, there is one crucial thing, one crucial concept about domain and range. And yeah, let me change the color. This is very important. Domain and range. Okay, suppose I have a relation that looks like this: a1 comma b1, a2 comma b2, and a3 comma b3. Then the set a1, a2, and a3 is called the domain of R, and the set b1, b2, b3 is called the range of R, the range of the relation. Okay, so it's nothing, it's just the first element of every tuple forms the domain, and the last element of every tuple forms the range of the relation R. It's nothing. It says that R is related from its domain to its range. That means it takes an element from its domain and then it images it to the range. Okay, so you can say like that. And yeah, so let me give you an example with numbers, right? So suppose this is a relation. So here the domain of R is 1 and 10, because the first element of the tuples are 1 and 10, and the range of R is 2 and 3. Okay, so yeah, simple as that. And there's another concept called the inverse relation. The inverse relation. Okay. If R is a relation, suppose a1 b1, a2 b2, and a3 b3, then R inverse will be the relation with the elements of tuple interchanged: b1 a1, b2 a2, and b3 a3. So yeah, this is the inverse relation. Okay, so R inverse is written in rooster form like this: is this for every a comma b, for all a comma b belongs to R. So this sign is named for all. Okay, so yeah, this is the inverse relation. And one thing you can guess that the domain of R inverse is the range of R, and the range of R inverse, is actually the domain of R, because the elements inside the tuples have interchanged, right? So yes, and that will be that. So that's all for today, and I have some practice problems and exercises. If any of you are interested in doing that, you feel free to contact me through my email. And if you are interested to collect the lecture note, and I don't think this will be much helpful, because you can find these things in any standard mathematics book, right? So yeah, So that's all for today. See you all again in the next lecture. Perhaps I'll be doing it in this week or the next week, and that lecture will be on functions. Okay, bye.